right, welcome back to The Grow, everybody. Today we are going to get a little sciencey. We are going to go over cations, anions, how they are uptaken, what purposes they serve, and what roles they play inside of our soil and soilless mediums. All right, so let's jump right into it. What are cations? Cations in soil are positively charged ions, often metallic. They serve as vital nutrient for plant growth. These ions play pivotal roles in supporting plant health by facilitating nutrient absorption, enzyme activity, and other critical physiological functions in the plant. So for an example, to get a cation, you would have to have an atom of a single metal. So we have, for example, we're going to use calcium as an example. So before calcium becomes a cation, it would start off as a calcium ion, and then it would actually have to lose 2 electrons to become a positively charged. So to become positive, you have to lose electrons. To become negatively charged, you have to gain electrons. So since calcium would then lose 2 electrons to become stable, it would become a positively charged ion. So as we lose our 2 electrons, calcium then would become calcium cation, which then is in an available form that the plant could actually uptake. So basically, once an atom of a metal becomes stable or loses its electron and becomes positive, then it becomes a cation. And so once it gets its positive charge and becomes a cation, then it is now in a plant available form. So cations, the easy way to remember it is just cat. Think of like a paw for positive. So cat, paw, positive. And so that's how you know that cations are always your positively charged ions. All right, so for another example, we have potassium, calcium, magnesium here. So before, these would just be potassium atom, calcium atom, and then a magnesium atom. But then as they would lose their electrons to be stable, so they actually lose their electrons or gain their electrons to stabilize themselves. So since these would then lose their electrons, so potassium would have to lose 1 electron to become positive. So then potassium atom would then become potassium cation. Same thing with calcium, because being a cation, once it loses its 2 electron becoming positive. And then magnesium also would have to lose 2 electrons to become positive, making it a magnesium cation. So then once they get their positive charge, now they are in a plant available form to where the plant can uptake them. But since they are positive, they are electrostatically attracted to your substrate or whatever type of medium you're growing in, because most likely your medium is negative charged. So your substrate is going to be negatively charged, and since the cation is positively charged, they will naturally want to attract to each other and then lock onto each other and hold on to make a bond. So once our calcium cation becomes positive and becomes a cation, then it is attracted and naturally attaches to our negatively charged substrate. All right, so now that we know that cations are naturally attracted to our negatively charged substrate because they are positively charged, we have something called C.E.C, or cation exchange capacity of our substrate. So what does that exactly mean? So our substrate is negatively charged, which means that it will naturally attract the positively charged cations, whether it's potassium, calcium, or magnesium. It's naturally going to attract them to each other to make a bond. So inside of your substrate, it has a maximum capacity of how many bonds it can hold. So basically the cation exchange capacity is how many cations the substrate can hold on to or create that bond of electrostatic attraction. So your exchange capacity is how many particles of cations your substrate can attach to and hold on to. So some substrates have higher amount of exchange capacity, so they can hold on to more positively charged cations in the substrate. And some have lower, which means that they won't be able to house as many positively charged cations, which means that the availability of nutrients is actually lower if you have a lower exchange capacity in your substrate. All right, so once we have our positively charged cations, like I said, they're then naturally attracted to our negatively charged substrate. So your substrate is usually negative charged 9 times out of 10. It can be positively charged, but for just namesakes, that we're just going to say that our substrate is negatively charged, because 9 times out of 10 it is. So basically we have our positively charged ion. So K is for potassium. So we have potassium ion that is now electrostatically attached to our negative negatively charged substrate. So once the potassium becomes a plant available form of potassium cation that the plant can then uptake, what happens is it gets attached to the substrate. So then we have to break this bond to make sure that the plant can then uptake the potassium cation. All right, so now that we know that our cation exchange capacity is how much cations our substrate can house, or how many bonds that they can make to hold onto these cations. So now that we know that our soil can only hold, or substrate can only hold a certain amount, how does our plant now uptake nutrients? So how does our plant get a hold of potassium, calcium, and magnesium if it is already in this bond with our negatively charged substrate? So we have to do something called displacement. So we have to displace this positively charged potassium cation away from our negatively charged substrate. So how do we displace this? We have to displace it with another positively charged ion. All right, so now that we know that we have our potassium in a form that the plant can uptake, but it is locked into a bond with our substrate because it is a positively charged ion that is now attached to a negatively charged substrate particle. So for the plant to uptake the potassium, even though it is now in an available form that the plant can uptake, we have to split this bond. So the plant naturally does this in a few different ways, but we're going to go over pretty much the majority way that the plant uptakes most of its nutrients. So imagine if the orange was roots of your plant. Inside of the roots, you have something called proton pumps that actually will pump out hydrogen protons that are positively charged. So you have H+, which are hydrogen protons positively charged. And then what they will do is they will do something called displacement of the potassium cation and then separate the bond. And then basically the hydrogen will take the place of the potassium, allowing the potassium to break away from the bond of the negatively charged substrate. Therefore, then the roots can uptake the potassium cation through ion channels in the root system. But the plant has to drop and release this proton of hydrogen ions to displace this bond so that the potassium is then unlocked and then in a plant available form that the plant can uptake and no longer locked into this bond here. Now that goes for all cations. So anything that is positively charged, this is usually the number one way how your plant uptakes that nutrients is through a process of displacement with hydrogen, positively charged hydrogen ions. So this could have been calcium, magnesium, or any other positively charged cation. This is the number one way how your plant will uptake that actual nutrients. Because just remember, cations are just the positively charged nutrients that your plants are going to uptake. All right, now that we know how the plant separates the nutrients from the substrate, what processes does the plant do to make sure it's releasing the right cations? So the regulation and release of hydrogen positive ions in response to various environmental cues and internal signals. It involves complex mechanisms and signal pathways. Generally, plants sense nutrient levels, soil pH, and determine and demand for specific ions. For example, when a plant detects a low concentration of particular cations in the soil, it may activate proton pumps in the root cells. These pumps actively transport hydrogen positive ions out of the root cells into the surrounding soil, creating an acidic environment. This acidity facilitates the exchange of hydrogen plus ions with the soil particles, releasing the desired cations for absorption by the plant. The plant's ability to respond to environmental stimuli and adjust its ions exchange processes is critical for optimizing nutrient uptake and ensuring the growth and development of the plant. So basically, by changing the acidity level around the rhizosphere, when it releases these hydrogen protons, will then release what certain nutrients it wants from the substrate. So if it wants to release calcium and not potassium, it will release the hydrogen at a different acidity level to release calcium and keep the potassium locked into the substrate. So, and it will do this on terms of what kind of nutrients it needs, the environment around it. So that is one way how the plant can decipher between releasing what cations it wants to uptake. And that is one reason why growers stress so highly on pH, because if the pH of your substrate is off, then when the plant releases those hydrogen atoms or hydrogen ions at a certain pH level, if the soil pH is off, then the pH around the rhizosphere will not be correct either, which will be stopping the plant's uptake of the certain cations it wants to unlock from the substrate. So that is why soil pH is so critical. Now remember, like I said, that sometimes this is not always how the plant uptakes nutrients. Sometimes microbiology will break down these bonds and then the plant can uptake it that way. That's why organic growers can get away with not pHing so critically, but anyone who grows hydroponically and this is their main way of uptaking nutrients, that is why pH is so critical when it comes to hydroponic or synthetic nutrients.